Okay, in this lecture, we're going to talk about the 4 factors that affect reaction rate. And you can see them here on your screen. These 4 are temperature, frequency of collisions, orientation of molecules, and energy. And so let's just jump into the first one, temperature. Okay, generally as temperature increases, the rate of the reaction increases. And that's visually shown here with some glow sticks. These glow sticks work when you break them, you're cracking this plastic that separates 2 chemicals that mix. There's also a dye in there that's fluorescent. And so when the reaction happens and this energy is released, it lights up and you see it glowing. And so in hot water, the reaction happens much, much faster and more energy is released per unit of time. So it glows more, that energy is given off. In cold water, not given off nearly as much, right? You can put these things in the microwave and they'll glow really, really hot, but definitely don't do that because they'll tend to explode and a lot of people have been burned. So don't do that, but you can put them in like some warm water versus cold water to do something like this. Now, we've talked a lot in the past about rate laws. Okay, and the fact that a rate law is telling you an equation for how fast the reaction happens, and it depends on a rate constant and the concentration of reactant. So if this reaction here is A plus B goes to C plus D, the reactants only appear in this rate law. But it's not clear what powers these are to, and you have to do experimental kinetics to figure that out, whether it's first order, second order, 0th order, and you can go back to our previous lectures to learn more about that. Now, where does temperature come into this speed of reaction? Here's the rate, here's the speed of the reaction. It definitely depends on concentration, but this K must have the temperature dependence inside of it. So it's the rate constant actually, and we'll talk more about this later, that is temperature dependent, and it increases as the temperature increases. So if you had a plot here of rate constant versus temperature, okay, it might look something like this. Here it is at, 190 Celsius. Here it is at 210. Here it is at 230 and 250, etc., etc. And it actually gets quite exponential. So there's an exponential growth here of the rate constant. This should probably be a little bit lower here as a function of temperature. So as temperature increases, the rate constant increases, right? And it about doubles with every 10-degree rise or so. Okay, there's this exponential relationship. So as we increase the temperature, the rate constant goes up, so the rate goes up. There's a direct relationship there. The second thing that affects the rate of a reaction that we're going to talk about today are the frequency of collisions. And this is all based on sort of a collision model of kinetic molecular theory. So a lot of times we think about this in the gas phase, although you can think about it instead in the solution phase if you'd like. But we have kinetic gas theory, here termed more broadly kinetic molecular theory. You can think about molecules bouncing around in the gas phase off the sides of the container, right? Molecules must collide to react. So if there's molecule A, right, and here's molecule B, eventually molecule B and molecule A must meet up to react. There has to be this collision. Okay? If there are more collisions, more reactions can occur. So it's no surprise here that the rate of the reaction should be dependent on the frequency of collisions. So sort of tied into this is the fact that, well, the more molecules there are, right, the more collisions there will be, the faster the reaction will happen. Alongside, if the temperature is higher, the molecules move faster, right? So if these gas molecules are really rattling around, bouncing all around this, they're going to be colliding with each other much more frequently. So again, a higher rate of reaction. So all these things are kind of related, but we do like to sort of parse them out differently when we're talking about temperature versus frequency of collisions versus orientation, although they're all kind of related, as you can see, right? The higher the temperature, the faster the molecules move, the more collisions there are going to be. Now, talking about these collisions, it might not be enough that A and B meet up, okay? Here, if we assume they're just both atoms and they have to collide, maybe that's enough for the reaction to happen. But you could think about some more complicated chemical, some molecule, right? That is two atoms attached to one another. And maybe it's the case that if molecule B sort of meets up with them in the middle, no reaction might happen. But if molecule B meets up with them on the end and collides, maybe that's when a reaction can happen. The point here I'm trying to make is that orientation is important. So it's not only enough that they collide together, right? Sometimes it's also necessary that they are oriented correctly. And that sort of brings us to a third example here of something that affects reaction rate. So consider chlorine atom being here in red, and it's trying to meet up with this compound, N, nitrogen, O, oxygen, Cl, chlorine. Okay? So if this reaction is going to occur where the products are nitric oxide NO plus chlorine gas, how am I going to get Cl2? Well, it's probably not going to happen if the chlorine directly bumps into the nitrogen, right? It seems to make sense that in order for a chlorine molecule to form, the chlorine probably has to bump into the other chlorine. Okay, so it depends on what side the collision happens on. This is sort of a prototypical example of this orientation affecting reaction. Okay, you can see it sort of shown down here a little bit more illustrated much better than I could in this figure that was nicely made by a friend. Sometimes the molecules will collide and no reaction will occur. Okay. Ineffective orientational collision. The chlorine here is not colliding with the chlorine. It's colliding with the nitrogen or the oxygen. Okay, so they collide and they bounce off each other, right? But aligning the molecules properly can lead to a chemical reaction. So here's chlorine atom colliding with the chlorine atom, and now you can get a chlorine 2 in the end, as well as this nitric oxide molecule. Okay, now what I'm kind of glossing over here is that there are chemical bonds that have to be broken and reformed during this process. So it's not enough to just say that the things collide and the orientation is right, but you must have enough energy to actually break this chemical bond right here between Cl and N. Okay. And so that really hints at the fourth factor that affects our reaction rate: energy. Okay, we've talked about temperature. We've talked about frequency of collision. So temperature, as that increases, rate constant increases, right? And the rate constant is in the rate law. Frequency of collisions is important because you need things to collide for a reaction to happen. The orientation now we see matters. And the last thing that matters is energy, right? Because maybe the molecules are colliding in the right orientation, but if there's not enough energy to break this chemical bond, then they'll just bounce off of each other and fly apart. Okay, so that's the last thing we're talking about here, is an energy necessary for the reaction to happen. And usually we talk about this in terms of activation energy, right? The minimum energy needed for a reaction to take place. Okay, this sort of hill that you must get over to get to the products. Okay, in much the same way that if you were rolling a ball and trying to get it over this hill, well, you must, roll the ball towards the hill with a certain amount of momentum or energy. Otherwise, it gets right here and then turns back around, right? In much the same way, if the reactants are colliding but not with enough energy, they won't make products. They'll just bounce off of each other and roll back down the hill towards reactants. So that's what we're talking about here. The activation energy is the energy necessary really to break those chemical bonds, right? To actually break apart, in this picture, hydrogen and chlorine gas to reform them as hydrochloric acid and hydrochloric acid, right? There's some minimum amount of collisional energy necessary for those bonds to break, okay? And when molecules are colliding and moving too slowly, then they don't have enough energy to break those bonds, and the reactants stay as reactants. The activated complex is this sort of pinnacle corresponding to the activation energy. Okay, so right here at the top, we'll call this the activated complex. Okay, that is sort of the maximum energy on this diagram, right? The reactants will continue to gain energy as they proceed towards each other, right? And towards the rearrangement, towards this activated complex, also called the transition state. That is this maximum energy state, right? Where the organization of atoms is at this highest state, that's the activated complex, that's the transition state. We use these terms pretty interchangeably here, so activated complex or transition state. Okay, because it's transitioning from reactants to products. Now, the plot shown here I want to dig into a little bit more, okay? Starting off with reactants, they must collide with a certain activation energy necessary to break chemical bonds and reform new chemical bonds between H and Cl to give us two hydrochloric acids from hydrogen gas and chlorine gas. Okay, so this plot right here is usually called a potential energy surface. Okay, because it is about sort of the potential energy, more about the energy stored within the chemical bonds than it is about the kinetic energy of them slamming together, right? When they're slamming together, you're changing that kinetic energy of the collision into potential energy, that energy necessary to break and reform chemical bonds. Okay, so this potential energy surface here is the plot that's showing how the energy is possessed by the particles as the reaction proceeds. So moving left to right, the reactants gain energy, okay, and they're not really gaining, it's the kinetic energy being transformed into potential energy, but it's using that energy to move the atoms around and move them around in such a way that, you know, now the hydrogen that is bound to the other hydrogen is lining up, right, or getting close to the chlorine that is bound to the other chlorine, so that new bonds can be formed and other bonds can be broken. Okay, so a lot of times the reactants sort of have to move around, break some bonds before they reform other bonds, and there's some pinnacle in their energy. That is the transition state. Now, to label a couple things on this slide, this activation energy, sometimes you'll see that denoted with a delta or change in, right? EA for activation energy. And you might also see another double arrow from products to reactants. Okay, and this will be our delta H. Okay, we're familiar with this delta H of, you know, being an exothermic or endothermic reaction. Here, products are higher than reactants, so delta H is greater than 0. So this is endothermic. Okay, there's still an activation energy necessary to get to these endothermic products, but you can draw the same sort of diagram. Here would be the activation energy. And here would be the delta H, which is less than 0. Products minus reactants will give a negative number, right? Because this here is energy on this axis. Product energy is lower than reactants. We call this exothermic. Okay, and that excess energy a lot of times is released as heat. That's where the thermic comes in, exo releasing that heat. Now, you might also be asked sometimes, is the reverse reaction possible? Is it endothermic or exothermic? And I just want to make sure we understand that there's this microscopic reversibility, right? This notion that all reactions are reversible, right? This reactant going to product, if the activation is right and it can get over that hill, well, it's also possible for the products to go back towards reactants. So you could imagine that these two HCl molecules, you could play the movie in reverse. They could collide with the right orientation, with the right amount of activation energy to form H2 and Cl2. Okay, so although the overall reaction here is H2 plus Cl2 making 2 HCl's. You could have the reverse of this reaction happen as well. And a lot of times, actually, we'll draw double arrows for reactions to make sure we're clear that both of these things can happen. Now, the activation energy will be different, right? The activation energy here of the reverse reaction would be relative to products, where the activation here is relative to reactants. So the activation energy here is about this for the reverse. So I can label this the activation energy of the reverse reaction. Now, let's put some of this terminology into work, into practice, and try to solve this problem. Feel free to pause the video here and try it yourself. Otherwise, I'm just going to move forward and solve it. Okay, a few things before we actually answer this. This is just another potential energy surface, this transition state or activated complex. But now you see there's two activated complexes, right? There's two transition states here. That's fine. You can have 2, 3, 4 transition states. A lot of our diagrams, especially the ones we learn at first, only have one activation energy or one transition state. But a whole lot of chemistry actually has multiple transition states. And those transition states will be separated by an intermediate. Okay, so an intermediate, and we'll talk about this more in future lectures, an intermediate is something that's formed in the first part of the reaction that is then consumed later. It doesn't appear in the overall reaction, but it does take place in the reaction. Okay, so let's think about this question now. Imagine a molecule is sitting in the intermediate valley, so our reaction has proceeded and it's gotten to here. Okay, but my microscopic reversibility says I can actually go back towards reactants, or I can go forwards to product, right? Which is going to be easier, to convert the intermediate into reactants or to convert it into products? Okay, and it turns out that it's a matter of activation energy, right? You can look at the activation energy on the left, on the right, going to products, versus on the left, going back to reactants, right? So this activation energy, EA, I'll say for reactants, R here, is much greater than the activation energy here, EA for products, EAP. Okay, so in general, it's important to remember, right, that lower activation energy means a faster rate. Okay, now, the last couple concepts we have to discuss in this lecture sort of get all of the information we've learned thus far: temperature, orientation, collisions, activation energy, all those factors that affect the rate, and sort of smush them together into a quantitative relationship. Because it's important to understand the concepts of what happens and why, but we also want to be able to quantify this, okay? And in order to quantify this, let's first review this graph on the right that we've talked about at frequent times during lectures on intermolecular forces and solvation, but it makes an appearance here again. Okay, we've talked about it in the past as thinking about a liquid, say water, and thinking about the gas that sort of evolves above the liquid. How many of these water molecules in the liquid phase have enough energy to leave the hydrogen bonding network and go into the gas phase and create a vapor that then gives us a vapor pressure? Okay, we've talked about that in previous lectures, but there was still this kind of relationship involved. And it's involved here, as we'll see in a second. What this is showing is the number of molecules in our distribution, so out of all of our water molecules, okay, as a function of temperature, how many molecules have a certain energy? And maybe the dashed line here in our vapor pressure example is the energy required to overcome the hydrogen bonds in the liquid phase. And so at a low temperature, there's almost no molecules, just this little fraction of molecules that have enough energy to overcome the hydrogen bonds, meaning they can leap into the gas phase. But as I raise the temperature, now there's a much greater proportion that have that much energy. Okay? In much the same way, what we're going to talk about here is that in considering a chemical reaction, there's going to be some activation energy, E sub A. And as a function of temperature, right, more of the molecules and more of the molecules that are colliding, if I raise the temperature, will have more than enough energy to react. So if you think about, the gases in the room around you or the gases in some closed vessel, right, there is some temperature, maybe it's 300 Kelvin, but there's still a distribution of energies, right? Not all the molecules are traveling the same speed. Some are going slow, some are going medium, some are going fast. Okay, even at 300 Kelvin, because that is an average kinetic energy. So gases have this average kinetic energy called temperature, but each molecule has its own energy, and some of those will be going fast enough to react. And as I go from 300 to 500 to 700, more and more of the molecules are getting enough energy to have enough energy in collision to rearrange bonds and make products. Okay, so at higher temperatures, more molecules possess the energy needed for the reaction to occur. Okay, which means then they can go on and react, they can break those bonds and form products. Right, so if more have the necessary activation energy, right, then the rate increases. Now, mathematically, the number of molecules displayed here and shaded in red for high temperature or shaded in blue here, right, is quantified. And the fraction, we'll say, fraction of molecules with an energy that is greater than the activation energy, meaning they can get over that hill, they can form products, okay, is going to be equal to, or I should probably say proportional to, an exponential relationship that depends on this activation energy, that depends on this gas constant R we've seen before, and depends on the temperature. Okay, so here we see temperature and activation energy, two of the things that we have talked about affecting the rate. Okay, R here is our gas constant. There are various ones with various units, but we could say 8.314 joules per mole Kelvin might be the one you want to use. Depends on the other units you have, of course, right? Temperature is probably going to be in Kelvin. Activation energy is probably going to be joules per mole, so it makes sense to use that R. So this relationship that describes how many of the molecules that are colliding with enough energy to get over this transition state, right, to go to products, that all should be encompassed somewhere in your rate law, right? Because a rate law is telling you how fast the reaction is. And yet rate laws look disturbingly simple, like maybe this. So how is the rate of reaction depending on the concentration and depending on all this? Well, it must be that the rate constant is what we're talking about here, okay? So this K, this K is going to be proportional to these things, right? And it turns out that this was actually derived, although conceptually it makes sense, it was derived empirically from experimental data by one Swedish scientist named Arrhenius. Okay, and Arrhenius made some measurements and figured out pretty much all of this in the late 1800s. Right? He also did a lot of things, interestingly enough, and after the Industrial Revolution, he calculated that carbon dioxide emissions from all this Industrial Revolution would become a problem in raising the temperature of the climate, i.e. global warming and climate change, and he worked all that out in the late 1800s, and he said, this carbon dioxide that we're emitting from all of these new industries, that's going to be a problem in 2,000 years. Okay? What he did not foresee is the continuous exponential growth of that industrialization, and it's more like 200 years we've gotten to that point where it's a real problem. But he was really the first to work on this greenhouse effect of carbon dioxide. Pretty neat. But he derived this equation shown here, although we'll expand on it a bit. he showed that the rate constant is not just e to the negative ea over RT, but there's this other a term here, okay, which I guess you could say stands for Arrhenius, but it really stands for a frequency factor. And we started off this lecture talking about the four things that matter, right? In this equation of the rate constant, temperature and activation is involved. So perhaps this Arrhenius factor A here, this frequency factor, encompasses frequency of collisions and orientations, and that's exactly what it is. This frequency factor accounts for how often do they collide, and for what proportion of those is the orientation correct. Okay, so that's what the frequency factor is all about. It's related to the frequency of the collisions and the probability that each collision there has the correct orientation. And it depends on the reaction. So this frequency factor is going to be unique to every reaction, just like our rate constant ends up being unique to every reaction, because each reaction has its own necessary activation energy for reaction. Okay, so all these things are related. The overall rate in our rate law, okay, even when it's simply written like this, K times concentration of A, maybe times concentration of B or something, right? That is a rate law, okay? The rate depends on collisions. It depends on orientation, okay? It depends on activation energy. It depends on temperature. And all of that is encompassed within this rate constant here, okay? All those things that are very specific to a certain reaction all get wrapped up inside this rate constant. Now, the really good thing about this is that this constant, which looks not that special, now we have an equation that is quite special. And it's quite special because we can figure out what the activation energy is for a reaction, right? It lets us determine this activation energy from experiments. Okay, the activation energy can be determined graphically by reorganizing this. And you'll notice this sort of y equals mx plus b notation. All we've done is rearrange this with some algebra to put it in a form that gives us something linear. And this should sound familiar based on the previous lectures we've done in kinetics, where we learned about reorganizing equations so that we can plot things to see if things are linear. It's a good test for whether something's first order reaction, second order reaction. We're also using it here now to see what is the activation energy, okay? And if we tabulate, right? If we do these experiments where we measure time versus concentration for a reaction. We've talked about this a lot in previous lectures, and we tally all this up and we figure out its first order. Great. Now we do it again at a different temperature and figure out the rate constant. So, right, usually we're running experiments where we're measuring time, 0, 10, 20 seconds, etc., and measuring the concentration. From all of that, we plot it and figure out the reaction's first order, and the rate constant is whatever it is. But now we can do all that same thing, and we run the rate constant once at a certain temperature, maybe 300 Kelvin. Now we do all that same stuff again, but at 400 Kelvin, and at 500 Kelvin, so on and so forth. And so we run each of these experiments to figure out the rate constant, as discussed in previous lectures, and we plot all of that in this manner. And when we do that, we get this straight line here. This is called an Arrhenius plot, where the slope is negative activation energy over the rate constant. Okay, and so this is exactly how I figure out the rate constant. I know R is always 8.314, so whatever the slope is, that's where I get the activation energy. Okay, so again, step 1, do experiments at one temperature. You vary the concentrations, you obtain the rate law, you obtain K. Then you change the temperature, right? Do the experiments, figure out your rate constant. Then you change the temperature again, figure out your rate constant. Then you plot each of these rate constants, actually the natural log of these rate constants, versus, this is t to the minus 1, 1 over t, so 1 over 300 Kelvin, 1 over 400 Kelvin, 1 over 500 Kelvin, that is the x coordinate. Natural log of rate constant is the y, and you'll get a linear relationship, the slope of which tells you the activation energy. And it seems a bit convoluted and you know, a whole bunch of trouble, but it really is, you know, giving us some molecular level detail of how much energy is needed to make and break bonds. And from that information, we can figure out how the atoms are moving around, right? We don't have great techniques to actually watch a movie in real time of how atoms move around, so this is how we have to figure it out. Now, if you don't have a whole bunch of K's and T's, which is better, you can, you know, make a pretty good assumption if you only know K at 2 different temperatures, right? You can rearrange this relationship and put it in a form like this. And this is one you'll often see. K1 at T1, K2 at T2. Plug all that in R and solve for activation energy. Okay, so this is a formula that you should be comfortable using, and you will get some practice using right now. Feel free to pause the video here and try this yourself before I go through and solve it. Okay, so imagine you're able to measure the rate constant of a reaction at 2 different temperatures, 298 Kelvin, 398 Kelvin, and you have these rate constants. What is the energy of activation for this reaction? And this is pretty much just plug and chug. This is the equation we're going to use right here. Okay, just make sure you're writing it down correctly. L1 or ln K1 over K2, right, is EA over R. Activation energy over R. 1 over T2 minus 1 over T1. Right, that's it right there. And now we're just going to plug each of these things in. We just want to be careful with units. Okay, so natural log of what is 1, what is 2? We can call this first one 1, this first one 2. It doesn't matter as long as, right, I'm keeping 298 with 1.36 and 323 with 2.72. It doesn't matter which one I call 1 and which one I call 2. But here I'll call the first one 1 and the second one 2. So ln of 1.36 times 10 to the negative 7, seconds to the minus 1, over K2, 2.72 times 10 to the negative 6, second to the minus 1, is the activation energy. That's what I'm after. Over 8.314 joules per mole Kelvin. All of that times 1 over T2, 323 Kelvin, minus 1 over 298 Kelvin. These were given in Kelvin. A lot may be given. A lot for these problems. A lot of the times the temperature will be given in degrees Celsius or degrees Fahrenheit. All right, so make sure you are doing the conversion. Always put these into Kelvin for sure. If you're given an energy of activation, it might be in joules, it might be in kilojoules. Make sure it matches joules if that's the R you're using. Okay. In any case, you can figure out all of this, right? You can figure out the right side. I think for all of this, it comes out to be something like negative 0.0002597, and all this natural log business gives us something that's like close to negative 3. So you combine all that and isolate for activation energy, and you get something like 96,000 joules or 96.0 kilojoules. Okay, so that's the number we should get in the end if we can do this basic algebraic rearrangement. So that's a practice problem using Arrhenius's relationship, right? We've covered today all these 4 factors and how they affect the reaction rate, whether it's temperature, this activation energy, or frequency of collisions and orientation, which are wrapped up in this frequency factor, and learn something conceptually about how reactants have to not only collide, but collide with enough energy and in the right orientation for products to form. Otherwise, it might just fall back apart into reactants. So that'll do it for this lecture. Next time we'll get into actual mechanisms, different types of unimolecular, bimolecular, termolecular reactions, and how we figure out the exact mechanistic steps of some overall reaction, and how that relates to catalysis and enzymes. But that'll do it for this lecture. See you next time.